Are there any sort of bureaucratic questions you want to ask me just at the moment? For instance, okay, let's just talk a little bit about the organisation. It's 4 lectures a week, okay? So it's 4 hours a week. There's 3 hours lecture and 1 hour tutorial. So Monday, Tuesday at 12 o'clock. Thursday there's a tutorial at 12 o'clock, and Thursday there's a lecture at 3. There'll also be a practical, I think on Wednesday from 1 to 3, okay, and that'll probably begin in week 3, this being week 1. Okay, so I know the mathematicians and emphasis people might have some issues with that, but let's see how it goes for a while. Okay, any questions about that kind of thing before we get down to business? Yes, sir. You will. There will be a little bit of a tutorial this week, yeah. But what there won't be, do you remember there was a bit of confusion yesterday about the fact that I might be taking a 2 o'clock lecture belonging to Dr. Kokoran? That's because we're doing a swap. So he will be taking the Thursday 3 o'clock lecture for this subject, 3D1. He will be taking it this Thursday. So MSIS and mathematicians, CSMers, there won't be a lecture in this subject on Thursday at 3 as there normally would. Instead it'll be taken by Dr. Kokoran for 3C1, I think is the code for his program. I actually don't know. I'm sorry, it's on the timetable, as best I can say. So just moving through this to find where we stopped yesterday. Course topics, okay? So just a little bit more of the old bureaucracy here. Coursework. Now this is a big deal, okay? So I want to tell you explicitly and definitely about coursework. There's going to be coursework. As you can see here, there's a tutorial every week on Thursday at 12. The location, I just can't remember. It may be in Ars an Firsig. It's on the timetable. There's going to be a 2-hour practical every week when we get started, which probably won't start until week 3. It might even be week 4 by the time we get down to business. And because of the size of the class, which is fantastic, it may be that we might have to break that out into 2 sessions in the week. We'll see how that goes in the next couple of days. The practicals are actually marked. So you have a 2-hour practical. You'll be given the assignment usually at the end of the week, on the Thursday of the week ahead of it. You have time over the weekend and the rest of the week and the weekend to figure out what you're going to do. You go in there, you do it, you get a mark for it at the end, you walk away. Okay, no handing in stuff afterwards. Now, there's actually this is incorrect, so I'd like you to just take note of it. It says practicals will be marked for continuous assessment, which will be worth up to 15%. It'll actually be worth up to 20% of your course mark. So perhaps you make that note, and if I can, I'll make a change to these overheads later. Up to 20% of your year-end mark. And I don't want to tell you exactly how much it is yet, because it will vary depending exactly on what practicals we get to do. Okay? Once again, I just want to say the coursework is very important. It's absolutely vital, because this stuff, as you may begin to appreciate when we get down to some of the detail in a few minutes, it's very logical. And you've seen it before. You've probably seen it in the Ladybird book of computers, and you'll certainly have seen a lot of talk about it in secondary school and in the media. The point is, though, that knowing about it and actually being good at it and doing it are really quite different. I don't want to be facetious, but it's almost like being an appreciator of music. You know, somebody who can appreciate a good tune or a well-organised or a nice band or something like that. And you say, oh yeah, I'm a real expert. I know the difference between Led Zeppelin and somebody else, right? Franz Ferdinand or something like that. Just to mention one. However, it's a very big difference between appreciating on the one hand and actually doing, constructing, making, writing, performing, if you like, music on the other. And you need to keep that in mind. This is very, very tricky stuff, and it seems logical, it is logical, but it's very tricky in detail. Okay? So the coursework is vital. And here is the sort of mandatory statement here. You must attend the practicals. If you don't attend the practicals sufficiently well, we reserve the right, in keeping with college regulations, to return NS. NS stands for non-satisfactory attendance at courses. And they have implications which you can read up about in the calendar if you wish, but they're pretty severe. They could include you not being allowed to sit exams in the summer, or all kinds of things like that. Not being allowed to proceed with your year. Okay, enough of that kind of stuff. Okay, a couple of references for books and textbooks. People gain a lot of comfort from having a textbook. And over the years, there are lots, like I said yesterday, there's lots of knowledge out there about teaching on the 68,000, and it follows there are lots and lots of books. Most of the books are aimed at American audiences, and they're very big, thick, detailed, books that are hard enough to carry around, never mind read through. Books that are aimed at a British audience tend to be much better. They're more compact, more concentrated, and generally better. And one is this Clements one here, Alan Clements. Okay, so have a look for that. Now, I'm not saying you should buy this textbook, but I'm saying go out and have a look, and if you can come across something like Clements' book, fine. There's another book by King and Knight. It's an old book. It's very thin, and it's something like Introduction to Programming with the 68,000, or 68,000 Programming Intro, or something like that. King and Knight, the two Ks. There's also some stuff, there's lots of stuff on the web. In general, you can Google 68,000 stuff, and you can also look on the website for this subject, and that's the URL for it there. Okay, so it's pretty logical when you think that this is a junior sophomore engineering subject. The engineering degree is called the BAI. Okay, that's its principal aim anyway. Okay, so let's get down to business here. Okay, so here's something that you might recognize. We're not going to go much further than this. Yes, sir.
Sorry, what programming language are we using?
We're using 68,000 assembly language, so we're using no high-level languages at all. But just to be clear about that, because it's a very good question, we're not doing Intel assembly language, we're not doing 6800 assembly language, we're not using x86 assembly language. You'll see lots of these things out there. We're using specifically 68,000, Motorola 68,000 assembly language. Okay? And please ask me questions as I go. Okay? You'll appear on the podcast, but that's okay. Now, this is the typical ladybird example of a computer system, and I don't mean to denigrate it by saying that, but it was originally designed, if that's the term. It's a design principle really, rather than an architecture, and the design principle can be stated pretty quickly, and it is to separate special purpose units into special purpose devices, or special functions into special purpose devices. So in the top left there we have the CPU, the central processing unit, which is where everything gets done. Okay, all the calculations are done, all the instructions are executed. And in fact, considerably more goes on in the CPU than just in executing instructions, as we'll see. But it's specialized. If you think you're designing the piece of hardware, if you're designing the CPU, you only have to worry about that. You have to worry about fetching, decoding, executing instructions, and dealing with the data that's required. Another component of a typical computer system is memory. Okay, memory is, again, hardware that has the property of being able to allow you to retrieve information in a particular way. So you can get information from the memory of the computer into the CPU. Now that information in a von Neumann machine can be data, typically, numbers or characters or arrays or whatever it happens to be, but it can also be the program itself. Okay, so that's one of the defining features of the Neumann architecture as opposed to other architectures. Data and instructions, data and programs can reside in the same component, the memory. Now there's two memory subsystems in this for the reason that most computers nowadays actually come with two fairly distinct kinds of memory in them, and maybe more, as we might see later in the course, but two fairly distinct subsystems. One being what's commonly called RAM, RAM. RAM stands for Random Access Memory, and it is a misnomer. Okay, and we'll talk a little bit more about it. ROM, ROM, is read-only memory, which is not a misnomer. So here's the deal. The trouble with memory generally is that when the machine is not powered, or when the battery goes down or you unplug it, memory forgets or loses its contents, right? So a question might be, how do you get a computer to start up when you power it up? Where is the program going to be if memory doesn't work? Okay, And that's generally, but not always, but that's generally the function of ROM. Read-only memory is memory that cannot be altered by the computer, which isn't much use, but it's memory that retains its contents even when the machine is powered off. That's its important thing. So typically what happens when a computer of any kind starts up, a program in ROM, in read-only memory, gets control of the machine in a manner that we will explain later. It gains control of the machine, takes it over, and boots it up. So very often it's called boot ROM or boot memory. Okay, so once the machine has powered up, then perhaps you'll be loading, or the machine will load programs that it's going to execute, or it'll load data that's going to execute, and that information is stored in RAM. RAM stands for random access memory, but actually what it really means is read and write memory, read-write memory, memory that you can put stuff into, that the computer can store stuff in and retrieve it back later. Remember now, ROM allows the computer to retrieve information only. It can't put anything out there, can't change it, and it doesn't forget what's there when it's powered off. But RAM then is a place where it can hold things temporarily. Remove the power though, and RAM forgets what's in it. Okay. So typically RAM is much cheaper than ROM. Okay. So when you buy a machine, you might buy a machine with say 512 megabytes of RAM or a gigabyte or 2 gigabytes now of RAM, and it might only have maybe 256 megabytes of RAM or less. Okay. ROM tends to be a bit more expensive. RAM then is a place, if you think of it like this, it's a place where in a mature and well-organized computer, like a desktop computer, for example, you'd expect that RAM is a place where you hold stuff temporarily for use, whether it's a program or pieces of data. Typically, your file structure, the file system that you get to know on a computer, is stored outside the computer system proper in something like a disk drive or on the network or something like that. Okay, so we have the CPU where everything gets done. We have memory where stuff gets stored. And then we have this other thing here, the peripheral interfaces. The peripheral interfaces, like I was saying yesterday, they have the physical job of mediating between some aspect of the outside world, as we call it, and the interior world of the computer. The interior world of the computer initially is a place where instructions get executed and data gets processed, right? So something in the outside world has to appear in that inside world as data. Okay, that's the function of the peripherals from a logical point of view. Physically, of course, they have to mediate say it's a temperature or high voltage or pressure or something like that that's maybe being monitored or being affected, and the peripheral interface has to do that. And I've just given you a couple of samples of peripherals that you might find on a desktop type or an office type computer. A screen and a keyboard, they're peripherals. Disk drive, that would be a peripheral. Network, say an Ethernet or a telephone network or something like that, that would be a peripheral. And the printers and so on, they would all be peripherals. Okay, so the peripheral interfaces, these are the things that we think of as the computer. Naively, you look at the computer and say, oh, that's the computer. But actually the computer is just the CPU, the memory, and the peripheral interfaces as they appear from the inside. Okay, so that's the von Neumann machine, the von Neumann machine. Von Neumann was I think he was Hungarian, but he is considered a physicist, an engineer, a mathematician, and a kind of a philosopher, depending on what you happen to be. If you're an engineer, he's an engineer, and so on. But a very smart guy to come up with this idea of partitioning the functions that are needed in a digital computer into special purpose components. Okay, so that's the von Neumann machine, and the 68,000 is actually a central processing unit in this kind of world. The 68,000 is a CPU. Okay, so the CPU then, there's a little bit of detail on these upcoming slides on what's what. The CPU is where all the work gets done. Now, what does that mean? Well, that's where the instructions get executed. You'll remember from yesterday that what we'll be doing is writing instructions in assembly language, each of which turns into a machine code instruction, and each machine code instruction is executed in the CPU. Now again, this is very logical. Like I was saying earlier, this is very logical. Yeah, we know that. Okay. What are the implications of it? The implications of it are pretty serious. There has to be hardware resources to execute those instructions. because we're at the level, we're at the ground floor. Okay, beneath us is the hardware, and above us is other software. So these instructions that are coming in, as it were, in the ground floor, they have to be executed by the hardware. They have to be effective in that algorithmic sense. Right? So that's the first implication. So if you have an instruction, there has to be a bit of hardware there to execute it. Okay? But even more, a program is a series of instructions, and they're usually instructions that are stored in memory one after another, sequentially in memory. Roughly speaking, that's the case. If that's the case, then if the instructions that are going to be executed in the CPU live in memory, in RAM we'll say, or ROM, then they have to come across that bus that I didn't mention. Oops. They have to come across that bus into the processor to be executed. So anytime an instruction is going to be executed, it has to be fetched across the bus, has to be brought into the CPU, it has to be put somewhere, it has to be deciphered or decoded by the hardware, and it has to be executed. Okay, it has to be given effect to. If the instruction uses data, the data must also be in the CPU. Okay, so there's a lot of implications from the simple idea that the CPU is where all the work is done. Instructions have to be fetched, data has to be fetched, the instructions get executed, and they get put away, or maybe the data gets put away back into memory again. So all that has to happen, it all has to be done by the engine inside the CPU. And we can think of the CPU as containing the resources needed for giving effect to the instruction set. For example, if an instruction set contains a multiply instruction, it has to have the hardware that will do multiplying. If it's got a thing called a barrel shifter, if it's got a fast shift instruction, it probably has to have a piece of hardware called a barrel shifter in it to do that very quickly, and so on. Now we're not going to get involved in that hardware, but I'm just saying it has to be there. Okay, so together all the instructions that the 68,000 or that the machine, the CPU is capable of executing are called its instruction set, and it's finite and it's small. Okay, so that means that you can't go along and while you're trying to write a program, dream up an instruction and say, oh, I think I need an instruction that multiplies by 2.5. Sorry guys, all you've got is the instructions that the hardware provides. Okay, now I'm being trite there, but nevertheless, people sometimes come on and say, oh, I thought we could invent any kind of an instruction. Okay, so the instruction set is the set of instructions that a particular make of CPU, a particular brand, a particular version of a CPU can recognize. So way back, like I was saying yesterday, the early computers had their own instruction sets. The IBM 360 was the first family of computers. Okay, whereas before the IBM 360 came along, you'd bring out a new computer, your IBM or Honeywell or General Electric or one of those. You bring out a new computer, and depending on the way you built that computer, and depending on the hardware resources you put into it, it'd have a particular instruction set because there's such an intimate connection between the instruction set and the hardware. In the IBM 360, they separated the hardware from the instruction set. And what they decided to do, presumably for corporate reasons, was to have a fairly fixed instruction set with different hardwares to implement it at different levels of performance, different speed or different cost, and so on. So the IBM 360 was the first time the idea of, and you'll probably come across it when you're out on the web, an instruction set architecture became a new idea. The instruction set architecture being distinct from the hardware architecture underneath it. Now once again, we in this course are not going to drop below the instruction set architecture. We'll be looking at the instruction set architecture of the 68,000. We won't really be looking into how it gets implemented underneath. But in different models of the 68,000 family, it gets implemented using slightly different forms of hardware. Just to go back to this idea of shifting, if you have a whole load of bits together in parallel, say 32 bits, and you want to shift them off to the right by 4-bit positions, you could either do that 1 bit at a time, taking 4 shift operations, and you could use the hardware for that, which would be relatively simple, or you could employ a barrel shifter, which is quite complicated and could move any number of bits in one go. Right? As far as the instruction is concerned, the instruction gets executed, but as far as the hardware is concerned, it'll either take 4 times longer if you don't have a barrel shifter, or it'll be much quicker if you do have a barrel shifter. Those kind of details are left underneath the instruction set architecture level. Anyway, so that's probably going a little bit too detailed at the moment. So a machine language program is actually the thing that you get from your compiler. You compile your, say, C program or your C or your C++ program. It gets turned into eventually a file of machine code, which is a machine language program, which will be loaded and executed by the machine. Okay, it's a set of instructions which utilize the CPU's resources, okay, to perform some specified tasks on data. It's very easy to forget about the data here. We're talking about instructions, we're talking about instruction executing hardware, we're talking about fetching instructions, but the data, how do we deal with the data? We'll come to that as well. Okay, memory. It's just a mechanism which information can be stored, and all you can do with memory is read information from it, and you need to know where it is somehow. You need to know where the information is. You need to know it's what we call its address or its location. So you can fetch information and you can store information if it's RAM. Okay, you can store information, so you can read and write information. What you can't do in a von Neumann architecture is do anything out there. You can't say take that number that's in that location and that number that's in that location and add them together out in memory. If you want to do something with them, you have to bring copies of them into memory, into the processor, perform the operation in the processor, and then possibly put the result back out there. Okay, so it's quite complicated to actually perform something as simple as just adding two numbers. But as far as the construction of the machine is concerned, memory is just a place where stuff gets stored and retrieved from. So it makes it easier to build memory. So nowadays you can relatively cheaply buy an absolutely enormous amount of memory, say a gigabyte of memory, which is probably more computer memory than was in the country of Ireland in 1985 or 86. I mean, it's an absolutely phenomenally large amount of memory. But it's not enough. It's never enough. What's going to be in memory? Well, as I said earlier, two kinds of things. Instructions, which form a program, and data. Now, when you look at memory in a typical computer, there are these tools that you can use to actually look at memory. These little programs you can use to say what's at this location and what's at that location. If you look into memory, all you'll see is binary patterns, bits. And you won't be able to tell a priori whether a particular sequence of bits in some part of memory actually correspond to data or instructions. Okay, so at that lowest level, I think it's fair to say no modern computer is typed. You know data typing in C and Java? No modern computer has data typing built into its hardware. There's a little bit of distinction made between instructions and data. And due to the problems with Microsoft Windows, these things have come to the fore recently. But we'll talk about them in the context of the 68,000 a little more later. Okay, but instructions and data is what's going to be in memory. Now, peripherals then are just these devices that are external to the computer system. So from our grandiose point of view, a computer is the CPU, memory, the peripherals looking from the inside, the bus that joins them up and over which information is transferred, and then there's all this other stuff, these peripherals that are out there. And the peripherals actually might be fairly sizable things. So many years ago, when I started working in this business, a telephone exchange, a complete telephone exchange, well, that was a peripheral to a computer. So you had this computer in a room which would be, let's say, a quarter the size of this room, and it was driving a machine that was could have been the size of the whole museum building. Okay? And yet, from the point of view of the programmers of the computer, it was a peripheral. Now, those days have, I think, more or less gone. Nevertheless, still, peripherals are considered, out there by programmers. Oh, yeah, sorry, and just I did say peripherals make it to the machine. If you look at a machine and you say, well, that's a machine that's a mobile telephone, for example, or this is a machine that happens to be the engine that moves a car along, and this other machine happens to be a desktop computer, and so on. The difference between those from a computational point of view is usually quite small. They'll all contain digital von Neumann computers, which will have, a CPU. They'll have memory. They'll have a bus system of some kind. And what will distinguish those machines from one another is the nature of their peripherals. But they'll all be run by von Neumann machines. So that's why I said peripherals make it to the machine. Okay. The CPU that's in this thing here is a CPU that was designed by Motorola, IBM, and Apple, more or less in that order. Well, actually, probably IBM were the lead designers. And the CPU in this, versions of it appear in car and truck engines, in some PAM devices, and so on. Okay, so the actual machine itself is determined by the peripherals, but it's still the same computer. You'd still be able to, if you picked up assembly language for the PowerPC chip that's in this, you would find it fairly straightforward to program in any of those machines. Right? You'd have to learn the details of that area, but that would be it. Embedded computers are simply computers that happen to be inside a machine, such as in a mobile phone or something like that, a washing machine, whatever. One of the things that's very important in the context of embedded computers turns out to be energy consumption, power consumption, for a number of reasons. One is the size of the battery and battery life, if it's a portable device, but also the amount of heat that is dissipated has to be dissipated into the environment, and if there's a lot of heat being generated, it's going to require special measures, such as perhaps a fan or something like that. And you have to be very careful about that. And it's a real big deal in some areas. And it means that when you're programming those devices, when you become skilled in programming, you might want to program them so that they execute the minimum number of instructions. Okay. So that the machine can go into a quiescent state and consume little or no energy while it's resting. Okay. To go on with our terminology a little bit, a microprocessor is a CPU on usually one chip nowadays. Okay. And so this is microprocessor systems. It could be called computer systems. This course could be called computer systems. When microprocessors came out first, they were very primitive, and there was a huge gap between a microprocessor and, say, a mainframe computer. That's gone now, and most computers would not be the architecture of most mainframe computers now would not be much different at all to some advanced microprocessors. So that's a microprocessor, and then a microcomputer. A microcomputer, well, a single-chip microcomputer is all the von Neumann machine plus some of the peripherals typically on a chip. So it'll have the CPU, it'll have memory, it'll usually have a mixture of RAM and ROM. It may have some special-purpose peripheral interface chip devices. For example, an analog-to-digital converter would be typical enough. And they'll all be integrated onto one chip, which you'll be able to buy for 50 cents or $1 or whatever. Okay, so that's a microcomputer. So that's what's before us, to get skill in these areas. Now, I think the first thing that we need to look at is number systems, right? Because we're going to be talking in binary initially. So what I was gonna do now for a few minutes is to talk about binary numbers. Now let's just begin with the notion of a byte. Okay, we're going to see that memory and therefore the rest of the computer is organized in handling groups of bits of information 8 at a time. Okay, so we'll have the notion, first of all, of a byte of information. We don't know what the information actually is, what the byte stands for, but it's going to be 8 bits, each of which could be a 1 or a 0. By the way, a bit is some tricky name for a binary digit. So 8 bits forms a byte. Okay. Now we're going to use bits and bytes and groups of bytes to represent any kind of data that we want to deal with, and also any kind of instruction that we want to deal with. But The byte, I suppose, is the fundamental component of the system. You can get underneath the byte, you can obviously pick out a bit, and you'd expect that you have instructions there to pick out a bit in a byte. But typically you can also think about a byte as two halves, each called nibbles. Okay, so there's two nibbles in a byte. And you will see that, I'm not making that terminology up, you will see that from time to time, a nibble. Okay. In the 68,000 world, in the Motorola 68,000 world, if you look at a group of bits there, say like this, let's say we have the group 10111010, we would normally look at that as the rightmost bit being the least significant bit and the leftmost being the most significant bit. Okay, the MSB and the least significant bit. Now this is an arbitrary convention, and other computer manufacturers look on these differently, but we're going to stay with this convention, which is kind of natural. Okay, this is the least significant bit is the rightmost bit as we would draw it, and the most significant bit is the leftmost bit as we would draw it. Okay. And by the way, you might notice that I'm grouping these in groups of 4. This is again a convention. You know, when you'd write a number like say 7,963, you're effectively grouping these digits in groups of 3 with a comma between them. Okay. Here, what we're doing is we're grouping the bits in groups of 4. We're leaving a little bit of a space between them, not a comma or anything like that, but just a little bit of a space, and you'll see why in a few minutes. Okay. So we would say this is bit number 0, and we say this is bit number 7. Okay, so we're 0-based bits. We're not saying that the first bit we're going to look at is indexed 1. We're saying the first bit we look at is indexed 0. So 0-based indexing is what we use. Now, can anybody tell me how many different things you could possibly represent with 1 byte of information? So you have 1 byte, you have 8 bits. How many distinct things could you represent? It's not a trick question. Anybody venture a guess? By the way, I'm looking for a wild-ass guess. I haven't told you the answer to this, so anything that you come up with is okay. Well, nearly anything. So just think about it now. How many distinct things could you represent with an 8-bit? To put it another way, suppose you had a gazillion things, and you wanted to be able to pick out one of them, right? How many different patterns of 8 bits could there be that would be distinct from one another? 256. That's the right answer. Why? Why did you come up with that answer? Or how did you? Not so much why. You've heard it before. Okay, thank you. Anybody else? I mean, it is the right answer, but why is that the right answer? Okay, yeah, exactly. So if you look at just 1 bit, it's got 2 possibilities, 0 or 1. If you look at 2 bits, it's got 0, 0, 0, 1, 1, 0, and 1, 1. And pretty soon you can come up with the pattern that it's 2 to the power of n, where n is the number of bits. Right? So that's the answer. Thanks very much. So 256. Okay, and that means that if you want to represent, say, a range of numbers, suppose you're using this group of bits to represent a numerical value. The maximum number of different values that you could represent is 256, which isn't a lot. So it does appear to follow that whatever we do, we're going to be grouping these things together in groups. Maybe we might have 2 bytes together, which, by the way, in the 68,000 world is called a word. Okay, 2 bytes is a word. You might want to note that down. And it's different from what a word is, say, on the Intel or the IBMs. Okay, so 2 bytes together is called a word. So a word then is 16 bits, and so you'd expect to be able to represent 2 to the power of 16 different things, 65,536. Okay, which is fine, and it's a bit more representative, perhaps, of the kind of range of numbers you might have to deal with. Okay, so these are the kind of things we have to begin to think about. We have bits, bytes, which is the sort of basic unit of storage in a machine. Words, 16 bits, and then the 68,000 also has the notion of what's called a long word. A long word, which, anybody guess what a long word might be? Okay, we're talking patterns here. 32 bits. Okay, so the 32-bit long word in the 68,000. Later versions of the 68,000 family deal with a thing called a quad word, which is 64 bits wide. 64 bits But the 68,000 itself has hardware, remember we're talking hardware here, has hardware that allows it to deal with bits, nibbles, bytes, words, and long words. Okay, more or less at one go. It doesn't have instructions that allow it to deal with a quad word at a time. Now, okay, so let's imagine that you're thinking about using bytes, whatever they represent, whether they represent numbers or instructions or characters or arrays or whatever it is, and you're thinking of dealing with them, of using them, again in hardware. One of the questions you might have is, how many bytes at a time can you deal with? Okay, can you deal with 1 byte? Can you just take 1 byte at a time? Is there space in the CPU for something that's 1 byte size, or 2 bytes wide, or 4 bytes wide, or 8 bytes wide, or what is the sort of natural size that the 68,000 or the processor can deal with? And of course, it varies from machine to machine. The very first microprocessor that I know of that came out could deal with units of 4 bits at a time, maximum. Okay, 1 nibble. It was 1 nibble wide. So that meant that if you had, say, a 16-bit quantity that you wanted to process in one of these things, it was going to take not less than 4 operations. Okay, 1 for each nibble. There's 4 nibbles across. Okay, so the width that the processor can deal with, the data width that it can deal with, is a big factor. So the very earliest processor was 4 bits wide. The first sort of major processor from Intel, the 8080, was 8 bits wide. The 8086, which was the processor that went in, or a version of which went into the IBM PC initially, is essentially a 16-bit processor. That is, it can deal with 2 bytes at a time. So for example, you could add 2 16-bit numbers together in one operation. The 68,000 is a 32-bit processor. So the 68,000 is 32 bits data machine. Okay, so it can handle 32-bit long words at a time. So you can tell the 68,000, get that long word from memory, get that other long word from memory, add them together in one operation. Okay. Now, subsequent machines, there are some 64-bit machines out there that are coming into use now. So, for example, recent versions of AMD's processors and recent versions of Intel processors are beginning to be 64-bit compliant or compatible. But it means that they can deal with 64-bit units of data at a time. IBM in the Mac there has had 64-bit processors for a little longer than both Intel and AMD, and they've been in use for a while. They're not in widespread use yet. The 68,000 though is 32 bits wide. So we would expect to see, would we not, therefore, that the 68,000's instruction set would allow us to talk about bytes or words or long words. And that is indeed the case. And let me give you an example of an instruction. Now we're jumping around a bit here, at least I'm jumping around here a little bit deliberately. Okay, we come back and look at all these in an orderly fashion, but I just want to give you a flavour of what we might be doing. We might say, for example, I want to move. So this would be an instruction. I want to move a word, and I want to move a word from one place to another. Oh, the next thing is, well, what are these places? Well, let's imagine. You remember I yesterday said that there's places in the processor for holding things temporarily, and they're called registers. Okay. Turns out that there are 16 of these registers in the machine, and we'll talk about them in detail. But one of them, well, I should say, one set of them are called data registers, another set are called address registers. So let's imagine that I wanted to move a word from, say, D0, data register 0, to address register 0. That's an instruction. Okay? So that would be okay. And you can see I'm specifying an operation, move. I'm specifying the size of the operation, byte, word, or long, with .w there. And I'm specifying 2 more pieces of information, the source and the destination. Now, the grammar, the syntax of these things is very peculiar when you come from C or Java. But this is actually valid syntax. Okay? And I should also say, by the way, that it's starting not in the leftmost column of the page, but typically in column 4 or column 8 or column 12 or something like that. So that's an instruction. Okay? Okay. So that's if the piece of information is in data register 0, we're copying it, we're moving a copy of it into address register 0. Let's imagine that we wanted to get something out of memory. So let's suppose we have something in memory. Well, we can think of it as a byte or a word or a long word. So the question is, how do we say where it is? What does it mean for something to be in memory in this world we're talking about? Well, the memory locations are each considered in the 68,000 to be byte-sized. Okay, so there are locations, each of which holds a byte of information, and the locations are numbered. They have addresses. Right? So we could say, I want to move a byte. Okay, 1 byte of information. So if I know the location, suppose I know the location is location 74. I could say I want to move a byte from location 74 into, say, suppose I want to add the number at location 74 to the number at location 75. Well, I'm going to load the number at 74 down into the computer's, one of the registers, let's say D1, happens to be free, let's say. I'm going to load it down there. I could load the other one. Into, say, D2. Okay, so I'm getting one number down from memory into a register because I want to do something with it. I'm getting another number down from memory into a register because I want to do something with it. And now I can perform an operation here, which would be add the byte, add dot B. So I have another instruction. So where am I getting these instructions from? I'll give you an instruction set in a couple of lectures' time, maybe even on next Monday. So I'm going to say I want to add the byte that's in D1 to the byte that's in D0, in D2. Sorry. Okay, so here I've taken copies of 2 numbers into the processor. I've added those 2 copies together. The result is in D2, and I could maybe store that back out again if I wanted the result to be, say, in location 76, for example. Okay, so it's a little bit of assembly language. A little bit of each of those statements gets translated into one machine code instruction. The amount of time it takes to execute these instructions, they're very quick. Now, in the 68,000, remember it came out in 1978 or 9. Each of these instructions would take of the order of a microsecond. That's a millionth of a second. Nowadays, on that thing there, and maybe on your own machines, it would take of the order of a nanosecond, a billionth of a second, to execute each of these instructions. Okay, so what we're talking about is 4 instructions, 4 billionths of a second, 4 nanoseconds, maybe, to execute that. And on a modern, very modern machine, it would probably be 2 to 3 times as fast as that. So we're talking at a very low level about the detailed execution of instructions in memory. So you say, gosh, if it takes 4 instructions just to add 2 numbers together, we're in for a hard time. And yes, the answer is yes. You need to make sure that if you're writing assembly language for commercial gain, that you restrict your use of it to the areas where it's going to be most used. Okay? So typically they'd be in parts of a program that are slowing the overall execution of the system down. Yes, sir?
What does 74 stand for?
What does 74 stand for? Well, these are, and I'm being unfair to you here, right? These are the locations of memory. So I'm saying, go to memory location number 74. Okay, and that's a byte. Pick the byte of information that's out of that, and put a copy of it here to D1. So I'm taking a copy of what's at D74, a copy of what's at 75, adding them together in these registers, and then putting the result back and just replacing whatever's at location 75 with this new value. Okay, we will talk more about it. Okay, so there is a syntactical issue there. Okay, you're full up. Okay, thanks for your attention. So there'll be a tutorial at 12 where we go. I'll get you to do some of this kind of stuff on Thursday, but there won't be a lecture in this on Thursday at 3. There'll be a one lecture instead. Yes, sir.
Actually adding 2 numbers together in the registers.
Sorry. Yes, I'll talk more about it again. But yeah, this is the source and this is the destination. It adds a 2 and replaces the destination. Good question. The contract.
No, Blanco, yeah.